Hello everyone. Today let's look at a simple problem, but we want to investigate this problem from multiple angles. So if we look at this schematics, we will notice, so here, this is the input pin, input group of input pin. We have 8 pins, which is so these pins are labeled by 0, 1, 2, 3, all the way to 7. That's a byte. However, if we trace these lines, we will notice, the first, it's LSB get transferred to the MSB of the output pin. And the MSB of the input pin is connected to the LSB of the output pin. That means in this 8-bit constructed byte, every single bit is like a mirrored. Suppose this is the one day at your work. Your PCB design layout engineer told you, we made a mistake. The input info, say for example from ADC. The ADC output is a byte. It's a flash, ultra fast 8-bit ADC. And by accident, the pins, the input data bus is all flipped. So can you fix this bug in firmware instead of respinning the PCB? Because obviously spinning a PCB is of much longer time than put a patch in the firmware. So how can we, as a firmware engineer, answer to this question? So that's the topic we are going to discuss today. Since we work on the topic of embedded study, let's instead of running things in the computer, which means the Intel or AMD processor centered computer, let's bring up an IDE for a embedded platform. And here the one I just chose is an STM32 from ST Microelectronics. It's a very popular platform. And here let's create a STM32 project, because I use this IDE. Say if we use the IDE, there's a lot of housekeeping project, like initialization of peripherals to its default state, and all these borrowing work. IDE can help us a lot. You see here it asks us to say let's make the selection, because we need to tell the system specifically which processor we are using. And here let's switch to baud selector. The difference between MCU selector and baud selector is if you're using a chip from ST Microelectronics, then that's the MCU. However, as soon I'll show you, what I have on my table is a EVK. That means it has tons of things pre-configured. So that's why I'm working on this baud selector. So on this baud right now on my table, this has 2 parts. The first is the JTAG, which is a hardware debugging. To be precise, this is an SWD interface debugging, but serves the same purpose for JTAG, which is a boundary scanning way of doing hardware debugging. And this little shielded box is a package. The chip with LoRa capability is already in this chip, so it's you can see it's a lot cleaner to use this prepackaged SOM solution. And this is obviously its antenna. So let's move forward. Make a name, say bit reverse, and And okay, we can say this is see this is I mentioned there is some underlying library. We can dive this. This is a heavy topic. Since we only do something really trivial. You see, it asks us, do you want me to help you get all these peripheral configured to its default stage? Yeah, please go do it. Otherwise, this is like even we do copy paste. This is like a very tedious effort. So let it finish, and we can because I already have the hardware connected. So after this thing finish its peripheral generation, we will first go launch it into the hardware. Just verify. This is like a hello world, like a do nothing, absolutely nothing, but just verify the compilation toolchain and the debug toolchain are working properly. Otherwise, don't bother. Move forward if the toolchain doesn't work. It's take a little bit longer than I expected, but that it's approaching. It's oh, by the way, this is a way for to graphically we can do all these configuration. Actually, any system, any we can say build it. Say build it. I say it's working. Any vendor nowadays they almost like a Texas Instrument, NXP. They all have something similar to this, like a graphical interface to help the user make this configuration. But fundamentally, it's the same. We still need to know why we want to make such configuration. So there's it helps a little bit. Okay, here we see the compilation successful, and this is a little bit of the information about the compiled ELF file, which is ARM standard. Okay, let's, as promised, let's download it and see how it goes. Because by default, this is going to first download this ELF file in the binary form to the system, to the hardware, to that little module, and started execution. And in the meantime, it will set a breakpoint after min function. I would expect things stop. Yes, bingo. Yeah, you see, this is right after min. This is the first line after the entry point of user code. But this is not accurate, because we can actually, even before the min function, we can find a way to do a lot of our own work. But that's let's put it aside for the time being. Okay, if until this moment I know I can debug things gradually and it works. Okay, now let's start to think about the logic. First, let's just think about something really naive, like the textbook approach, because we want to like start from the fundamental. Say when we have a when someone ask us, hey, go reverse the bits in a byte, every single bit, LSB putting the MSB and MSB in the LSB position. So how do we do it? Yes, there's many different files, but we can do at least do a in place. Without wasting extra memory. So let me first define the function. Okay, so the first point, why do I use this strange looking type? Why don't I just put a int Remember we mentioned we only have 8-bit, and 8-bit is a byte. So in C language, the reason you write in C language, you want to be type specific. So we know this is if I write an int, this is going to take us 4 bytes, which is a waste. You might think your computer has, for example, you might have 32 gigabytes of DDR, but in a embedded system, we often run into in a situation that the resources are very very limited. Think about it. How much RAM do we have in total? We have 20K, and 20K. If you think about in the PC world, is nothing. I mean, each page in the virtual memory management, each page is 4K, and this is like only five pages, and that's everything we have. We run operating system in this 20K within this small footage. So that means every byte it's precious. But that's why we want to be so clear, specific about reserving the resources. Okay. Let's again say first, because how do we want to do reverse bit? We want to use the C language capable of bit level operation. That means we can like a shift. Remember in digital logic we know this, like we can do shift left and shift right. Also the value we want to make it a circle back, etc. Right? In C we have this capability. So why not just use it? So let's create what we want to eventually return. So we want to do this shift and for 8 times, because each time we shift right, we push one the current LSB. Um, right? We want to do 8 times, so that's why this is from 0 to 7. This is what the loop goes through, right? So in each operation among these 8 attempt, what we want to do first, we want to first leave a space in the result in its LSB position, and we want to like push. This command is equivalent to say this implementation, but it's just less elegant. If you write a expression like this, people will say, "Oh, you're not a C programmer." You will, yeah, we will soon get used to this expression, because this really saves time. And this is equivalent result equal to this OR operation, right? Remember the C language, the C or C++ is all, it both provides this bit level manipulation, and here it comes handy, right? So every time we take the current input value, we take its least significant bit, and based on that we want to set the final result, the reverse order. And you see, now we have utilized the LSB of the input value. We don't need it anymore, right? What do? We shift to the right and push the LSB of the input value to just disappear, right? For that many times, for 8 times, then we get what's the final result, right? Okay, so because my function is going to be called later, so actually I don't need to define a prototype in a header file. Actually, that is a good habit when the project gets bigger and bigger. pay attention to this. When it says user code begin end, that means, hey, please put your code here, because if you don't do this, it's better after initialize clock. If we don't do that, things can be trickier, because next time you use this little tool to regenerate, you might overwrite. Your code may be overwritten. That is the least thing we want, right? So here, formally we need to have all these unit test stuff, but let's just start simple. Let's say assert reverse order, and this is a byte, right? We can say the hex number equals, right? So this is our, oops. This is our, at least this is not a formal test. It's just whether the basic logic, at least the first attempt to get it verified. Okay, let's compile. Does it compile? What does it say? It's undefined reference. This is what assert minus t. Okay, don't worry. Let's just right. What is the purpose here? We just want to verify it, right? Now we can set a breakpoint here, because then I need to look for which system, which header file, which framework of testing framework provide that assert. Obviously, it's not. Let me see what is in this min function. Does it provide some? Okay, forget it. Yeah, we did set a breakpoint here, right? So this is also, I wanna show you that it's this debugging feature, right? It's pretty handy. So see, it says it's being downloaded, and it take like 0.1 second to get everything flashed. Now the system pause and wait us for further command. So we can say, okay, here we go. Right? This is the correct answer, because we send oh yeah, it's gone, because this is in a stack, and we modify that value. And what we send f0. What we get is 0f. This is hex number 0f, and say binary number is a 00001111. So because this logic is too simple, it just doesn't bother like a further verification. So let's think is when every time this function get called, and we always do this for loop, is that a waste? What if this is you need to do this in every day, when every time a data become, for example, previously we were discussing ADC. When every time an ADC data is available, we want to do this conversion and do this calculation. That means we are doing it again and again and again for the same information repeatedly. So that's why these software people, they just say, they use the term, say, hey, do dynamic programming. Literally, it's a cache mechanism, right? So we can say just if we can declare a table of size. What is the maximum number of like a unique number of byte? 256. So this number which is equal to so this is the initialization. Okay, so it's initializes to 0, and we want to put this. We want to initialize this value. So we want to say which value get updated or not, right? This table, whether it's valid or not valid. Let's say 0 is uninitialized because we initialized everything to 0, right? Then we will say if we want to determine if your input value is 0, then we directly we say return 0 because we know that, right? So, and here is the part. What if your value is not 0? And let's see this if this table. Oh no, B. Pay attention. I always put this constant on the left hand side. That has a reason. Let me first handle if not 0. So that means the table, that means in our cache value, this is our cache, right? We already know this is why is capital? That means we return this value directly because this is how software people does this thing. Otherwise, we do this and update the cache value. Result, right? But remember, there's a bug, right? Here is a bug because this b value gets modified all the time. So that's why we need to back up this value, back up the original input, right? This is it's our original input value, which will be result. So in that sense, we can be certain that these tedious, you might think, wow, my CPU is fast, but if you imagine your CPU runs at, for example, 200 megahertz, well, that's a decent controller, ARM controller, like an M series controller. But my ADC samples at 10 megahertz. And how many clock cycles you have for each data being retrieved. So that's a lot of calculation. So that means in this logic, it's just it's like an O1 computation to get this done. And this is not the key information. In a real embedded engineer, we very often we run into the requirement. Hey dude, you have to design a system which is a real-time system. What does real-time mean? That means even though you only do these computation for once, but in real time there is a concept called hard real time. That means I want deterministic. And even if there is a single time, it violates the promise. Say within that time I get things done. Even it happened only once, it's disastrous. You have to promise me. Otherwise, your airplane may crash, the power plant may have something bad happen. In that sense, all these software tricks, it doesn't may make your delivery, make your design unusable. So what is the professional way in the embedded approach is instead of having this table, having this cache in with it like a build in the runtime. Okay, we should build this in the compile time, and okay, we can run this beforehand in the initialization code. That's fine because your main work, your this is a bare metal one, so your real work would happen here. And all these are initialization. It's fine for a system, even a hard real-time system, to take time to initialize. That's perfectly okay. But when things start to run, it has to keep its promise. A lot of so in that sense, think about it. Is it wise to even we can get it initialized, but remember, pay attention to our system. Yeah, not only I only have 20K of RAM, my entire code space, which is a flash, it's only 192K. You don't want to do like all these code logic? You are you seriously you wanna waste this precious time? Because every time you calculate the same result, are you sure you wanna make consume some of these? At least maybe you consume a 300 bytes of your code base to just implement this initialization. Um, uh, is it wise? This is point one, right? Point two. These 256 bytes, does it live in, does it eat away from this 220K, or you want to eat consume part of this 192K? Like this is obvious, right? Most likely we want things because we have a lot more flash, and for things compiled in the runtime, for things computed in the runtime, it's a variable, right? Variable, it has to be in the random access memory area, and it's only things you can declare a constant. Then your compilers will say, oh, this thing never change. So let me put in the code space, which is I have nearly 200 bytes for that purpose. How do I do it? The trick is, yeah, we don't need this anymore. So what do? We don't need this either. Let's create a file. Let's say in the source folder, let's create a source file, and let's name it lookup table.c. I use C because initially, remember when we create a project, we say this is a C file because then it will determine which which tool chain we either G++ or GCC is going to use to be compiled this thing. Okay, here is the a header file. Oh no, I take it back. It's a source file. It's not a header file. Then I want to put put the entire table, and obviously I do not have this table right now, but let's because we need to run this. Oh, I already deleted it. We should run that program in a PC and generate a table. So here, what I want to say is lookup table and this describes the variable type. So that means we need to, and this is the moment let's find whether we can just Google it and grab this data. Otherwise, we have to go back and forth to compute. Okay, I found one. So this is a table, a pre-computed table, and oh, copy it to some extra. You might. So here's a few questions. I mean, don't forget. Before I forget, it's like why I'm not creating a header file, but instead I use a C file. It's because when we have this C file later, when it say, what if these things are proprietary, and we want to distribute things in a object file fashion. For each platform, we generate an object file. We only release the object file. We don't release our source code. So in that case, say we can that's the trick. We put things in the header file. For this simple case, it's okay to put in header file or C files. It's the same. You just define a pragma in header. But this is generally speaking, this is a better practice to make it. Then we say, because this is the choose table, and right, we just say anytime we want to do the computation, say results, and we want to say again, use the same value, right? Let's say oh, there's a bug or typo or what? UHR. Oh yeah, of course. Because how would the compiler know you have something here, right? So and it's oh, there's another bug. This is oh, the header file. Right, we do need this to define the to make the system know how do we interpret this int type, but we still don't know well. Like the compiler, when it goes through this file, like converting to the object file, say, what does this mean? You didn't tell me. That's why we need to say say the area for declaration, yeah, private define that. Okay, private define fine. Did I forget to copy the const? Right, now it finds. So there's a warning, right? And this is expected warning because we didn't do anything with that result. And remember why we do all these efforts. We want this thing to not consuming our memory space. You see, here we can say how many data we take. We literally only consume 12 bytes out of that precious 20K, and that's something we want. Another way we can say let's we can actually open that map file, and this map file lives in this particular address, right? This address, if we say let's just bring up its resource. I want to look for want to show you where is the system address. Is this reference manual? Yeah. system memory organization. Memory map. Okay, this is perfect. Uh, you see here. Remember just now we saw that it's a o 08 and this is in the right 8 800 then 0000. Let's see. Right 800. This is a relative to the beginning of the first flash, which is that nearly 200k resource for constant for code. And with the relative offset of this much, we can find this is where we have our flash system memory. So our that no, that code area, that 256 k worth of data stored somewhere here, right? That's the trick as a embedded engineer we often encounter, because in whenever we go to say a little bit some advanced ARM processor, we will discover it has a memory management system. That's why here in the entire memory space, everything is a physical space. There's only one memory space. What we find in our say this map file, it's just a physical address, which is literally the process the CPU interprets sees. However, in slightly advanced processor, it opts into like make use of a virtual space. You might heard of this kind thing if you are Windows user, then occasionally you see the blue screen. It will say page fault. So that's the memory being corrupted. So, but for each program, what they see is a virtual memory. It's that virtual memory. There's a management, there's a I/O management, and for the mapping the program well virtual memory to the physical memory. So let's don't deviate too much. I mean, that's a whole lot different topic. But here, I think this is just a few a few level of consideration for this simple naive question. We can see, right. So far, we have investigated many different approaches to optimize this solution in the programmable fashion. What if, in fact, this project you need to push its performance to the extreme? You just need the very fast solution. In that sense, think about it. Even we consider all these cache solution, it still takes time, right? Because there's a code. Every line of code, it doesn't matter. You use C, you use C++, any standard of C or C++, you use Rust or Python. Fundamentally, these all get translated into instructions, the CPU specific instructions. And every instruction, it takes time to fetch the instruction, fetch the data. And through pipelines, these instructions get executed. And this all takes time. So what if we do want to push it another way further? How do we do it? That's the time we come back to the view in front of us. Some of you unfamiliar with this software, you might say, hey, this looks like a schematics, because I see flip-flop. I see these flip-flop, I see these buffers, and I see these wiring connections, but this is not things we normally so popular like Altium, like pads, like Synopsys schematics. or PCB design tool. What is this? So this is a software called Vivado from Xilinx or say AMD. It designed digital logic for this particular scenario, design purpose. You see, initially I used this diagram to explain, all right, hey, here's the problem, and so these wire get connected, get flipped, the bit order get reversed. So I'm using this diagram to explain the problem. But what if you just someone else for some other reason they need you to solve such a problem? Don't you like is that obvious? This if we have this logic implemented somehow, and it does the job just in one clock cycle. In one clock cycle, the entire bit get flipped. So this is the way. If we look at and we can even see, okay, how simple this code it looks like. This is only like a real functioning part is this single line of code. What it does is you see at the synchronized. This is a synchronous data transfer. So synchronized by a clock, and all these input, say input like a byte worth of bits, which is 8 bits, get concatenated in the reverse order. Because you see, usually the bit 7, the say when we occurs at the leftmost position, right? That's the MSB. However, the MSB appears at the MSB of the input bus occurs at the MSB of the output bus, right? The input 0 is the LSB of the input, and the output is having the everything reversed. So this is the way we can achieve at a one clock deterministic achieving the expected result. But in a non-negative integer number in this realm, there's a value smaller than 1, which is 0. Can we in a digital world means everything is synchronized with clock. Can we achieve 0 clock? Like it takes no time, just immediate available to convert this to do the bit reversing, bit order reversing. Yeah, that's also doable. So what we can find is we can modify this to be we can say assign. So don't worry about the exact grammar because this is a language called Verilog. And let me first start the implementation, and it take a little bit of time, then I can make the explanation. You see, previously we are doing we having the entire design implemented as a synchronous design, which means you see this column of 7 exact 0 to 7 8 flip-flop is like a D flip-flop. So that means at each clock rising edge, the input value get like reversed and latched, producing the output. So that takes 1 clock. However, in this revised design, we can see, oh, I don't even need a clock. So that means, you see, there's no clock signal anymore here. Previously here, there's a line, say, that's the clock as input signal. And we have a synchronous, say, at the rising edge. We do whatever operation, synchronous operation. But here, you once this synthesis get completed, we will find, oh, this is a pure combination logic. That means it doesn't take any clock cycle. It happens instantaneously. And yeah, that's the ultimate approach to get the fastest implementation. And we may say, why bother we want this super like a super fast solution? Uh, uh, an easy metaphor to understand this problem is, say, in this age of AI, we often hear the word of AI accelerator. Say when we do inference, we may say, hey, why not use a GPU or use a like a GPU to get the inference job done? But in many occasions, a hardware implementation is way faster. Or say power consumption per T-flop wise, these application specific hardware design is magnitude level power efficient. So and also we don't even need to mention the speed is also faster because this you can imagine when we can in this ASIC we can design things in running in parallel. But here I'm just want to use this simple example to let us have a basic idea. It's not always necessary to have some C code or say some Python code to implement an algorithm. That could be the ultimate solution of hardware implementation. And this is your, we can say, hardware accelerator for this particular algorithm. Let's see. Okay, here we have the design finished, and let's oh no, it's the I see here it's still running. Let's wait a little bit. Because this is outdated. This is the old one. Let's close this design. Okay, it take a while to get this compiled. And here we can say, oh, this is the silicon, the physical deployment of the logic into different segments. But this is because this design is really really simple. We can't in such a huge chip we can't see it. So now we look into the schematics view of this design. We can see what's the difference. Previously, when we use synchronous design, there is a flip-flop in each pass, right? But here, if we look at, you see, this is a buffer, which is a combination logic, and the trace goes directly to the output buffer, which is also like a non-synchronous output, and so this confirms, all right, your input, whatever input information shows up in my input port instantaneously. Of course, there's propagation delay. But that's a different topic. Shows is there's no say clock synchronizations to say, all right, your input is only going to appear at output. The next clock cycle. Here, it happens immediately. So with this in being covered, we can conclude today's topic. So in this the takeaway, we can say to solve for example a algorithm like flip a bit, we can do the traditional software approach. We can use dynamic programming, or in the software people's term, we can do dynamic programming and using cache to make the computation more efficient. Or we can use a more, say, formula equivalence of the cache, and we can use a lookup table. And ultimately, this is the final solution of hardware acceleration. So I hope you guys all enjoy this thought process, and have a nice day, everyone.